Luffy has invented Gear 2 in order to encounter stronger enemy. However, it is too hot while launching Gear 2. He needs to increase the rate of releasing heat in his body. Suddenly, he has an idea, which is introducing fin on his body. Gomu Gomu no Fin! So now we need to teach Luffy fin equation so that Luffy can know how many fins he needs during different battles. First, we look at general solution, which is theta s equal to c1 times exponential ms plus c2 times exponential negative ms. There are four possible situations at the fin tip we will encounter. The first one is infinitely long fin, which the temperature at fin tip is equal to the temperature at ambient air. The second one is negligible heat loss from the fin tip, or we can say it is adiabatic fin tip, which means the rate of heat transfer at the fin tip is equal to 0. The third one is specified temperature, where the temperature at the fin tip is equal to a specific temperature. Number 4 is convection from fin tip, where the convection occurs at the fin tip. Now we look at the derivation of first condition, which is infinitely long fin. First, boundary condition is theta L equal to 0, which means TL minus T infinity. And also theta 0 equal to TB minus T infinity, or we let it be theta B. And from the boundary condition, we could get C1 equal to 0 and C2 equal to theta B. And we substitute C1 and C2 into general solution, we will get theta S equal to theta B times exponential negative ms. From the equation that we found just now, we will get the temperature equation after rearranging. Then we differentiate the temperature equation in order to get a new equations, so that we could place it into the rate of heat transfer at the long fin. And finally, we will get the equations for the rate of heat transfer. For the second derivation is about the negligible heat loss from the fin tip. First, look at the boundary conditions, same as just now. Theta 0 equal to Tb minus T infinity, let it be theta B. And the second boundary condition is d theta over ds is equal to 0 when s tends to L. From the boundary condition, we will get C1 equal to theta B minus C2, and from the second boundary condition, we will get the equation 2. Then we substitute equation 1 into equation 2 in order to get C2. And from the equation 1, we substitute the C2 into it and to obtain C1. After that, substitute C1 and C2 into general solutions and rearrange it. After rearranging, we will get the temperature equations Tx, and we differentiate it to obtain the new equations. Then we substitute into the heat transfer rate equations in order to obtain the final equation of rate of heat transfer for adiabatic heat. For the specified temperature, its boundary condition is theta 0 equal to Tb minus T infinity equal to theta B, and for the second boundary condition is theta L equal to TL minus T infinity equal to theta L. From the boundary condition, we will get the first equation and the second equations. And from the first equation, we need to times the whole equation to exponential ml in order to get the equation 3. Then we do the simultaneous equation by using the equation 3 minus to equation 2 in order to find the C2. And we substitute C2 into equation 1 to get C1. After that, we substitute C1 and C2 into general solution in order to get the temperature equation Tx. And then same procedure, we differentiate the temperature equation in order to get the expression of dT over ds, so that it can be plugged into the equation of rate of heat transfer for specified temperature, and finally we will get the new equations for the rate of heat transfer for specified temperature. Finally, conversion from fin tip. Its boundary condition is theta 0 equal to Tb minus T infinity equal to theta b, and negative Ka times dt over ds equal to Ha bracket TL minus T infinity with the condition S tends to L. From the general equations, it is rearrange it in terms of Ts. Then the expression is differentiated so that it can be used in the second boundary conditions. From the boundary condition, we will get the equation 1, which is C1 plus C2 equal to theta b, and by plugging in the dt over ds we found just now into the second boundary condition, we will get the expression of C1 in terms of C2 and other unknowns as the second equation. Then we substitute the second equation into the first one. Then we will get the expressions for C2, and then we substitute the expression of C2 into equation 1, we will get the expressions for C1. After that, we substitute C1 and C2 into general solutions in order to get the temperature equations. After that, same procedure, we differentiate the temperature equations in order to obtain the expression to substitute into the rate of heat transfer for convections, and finally we get the equations. And finally, Luffy is ready to fight his next enemy. Thanks for watching.